About to start the last afternoon of this conference week with Daniel Tubbenhauer, who's going to speak about webs and q-Howe dualities in types B, C, and D.
Thank you very much, Joel, for the introduction, and I also would like to thank the organizers for putting us all together to such a great event, and for giving me the opportunity to speak, and for putting me exactly at the right spot. Namely, after Red Miller, you will actually see why in some slides, in a few slides. Yes, so as Joel already said, I'm going to talk about some webs. We have seen several webs turning up in various talks, and we have also seen Howe duality, at least implicitly, turning up in various talks as well. And yeah, all of it, this is something I should mention, all of it I'm going to say is joint work with Antonio, and is based on joint work with Dave, Pedro, and Paul, who are all in the audience. Sadly, Antonio is not here. But anyway, so the name of the conference is something like Quantum Topology in Categorified Representation Theory. So let me just start with the motivation of this project, because I will neither show you quantum topology nor categorified representation theory. But the main idea which really started this project was this really beautiful story we already know in type A. And so relating various invariants like Reshetikhin-derived polynomials and Kovanov-Rosansky and Humphrey homology, which Pedro actually gave exactly the right slide. His first slide was somehow the Humphrey homology sitting in the middle, and around it there were various fields of mathematics and even physics which are connected to this Humphrey homology. So a natural question for me would be, well, there are also Reshetikhin-derived polynomials, and the corresponding Humphrey is in type BCD is called Kaufmann. There are also these polynomials in types BCD. So what actually can we do outside of type A to, well, define, study, try to understand this invariance, and hopefully in the long run have stories very parallel to what we have seen in the last few days, like spectral sequences or whatever, relations to geometry. And one of the main ideas of Antonio's actually was, well, Howe duality turned out to be very useful in the last few years in studying these invariants. For example, it is one of the main ingredients of our proof of functoriality in the end that Paul was talking about on Tuesday. And what it basically does is it gives you some web calculus, okay? And then from the web calculus, for instance, we have seen it in Dave's talk, you can somehow cook up those various invariants. And we just wanted to play the same game in types BCD, because as I'm going to explain, Howe just gives us a huge list of those dualities, and he's not stopping it in type A. So the main idea was somehow to take those list of dualities, to produce some web calculus very similar to Kupperberg, and very similar to what we have seen during the week. Try to get some web calculi, and in the end try to define those invariants and try to say something interesting, meaningful about them. So that was the plan. It was a very nice plan. However, it turns out it doesn't work. So actually I could stop giving my talk here. Instead, I think I decided to show you actually what works. So what Howe duality really gives you outside of type A. And there will be some, in my opinion, interesting new features or flaws or whatever you want to call them turning up. Okay. So this is the plan for today. I will explain the type A story yet again. We have seen several of those calculus before, but in contrast to Red Miller, I never get sick of drawing those diagrams, and I also never get sick of showing those diagrams. So actually we'll show you the classical diagrams, which I contribute to some of my heroes. So this is also a story about my heroes. Here we have 3 of them, Schur, Weil, and Bauer. We'll come to this in a few slides. And after I'm done with type A, which is well, explaining Howe duality. I will explain the type BCD story. And up to this point, there will be no quantum, and everything will go through smoothly. Very smoothly, very nice. And I was very happy. So actually, the whole project started while I was visiting Antonio in Freiburg. And we somehow thought, well, let's just do the diagrammatics. And as soon as we have diagrammatics, everything will work. And we were able to go up to this point here within, well, 1 day of work. We were very happy, and we thought, well, you just put in the quantum. It will work. Well, used to type A, it will work. So the last point, I will tell you what actually goes wrong if you want to try to put in the quantum case. And also, of course, you want quantum for link invariance. Also goes wrong. And it took us roughly 1.5 years to work out the third part, so the quantum story. But anyway, let me just go through it slowly. So the last day of the conference, so I will start with some history of the field. So one of my really favorite main tools in representation theory in general is what is called Schur duality, or Chauval duality sometimes, which actually goes back 120 years ago, basically, to work of Schur, who worked it out in his thesis, and it just says, take GLN, take Sn, the symmetric group, somehow the only really things we understand, right? And take the vector representation of GLN, which in my notation will always be V, so those V's will always be some vector representations, and tensor it k times. Okay? So this guy is, well, the universal is in Hopf algebra, so you get an action of the tensor on the tensor product. In the same way, well, this guy just permutes the tensor factors. And Schur then said, okay, these two actions commute. But before I get into this, let me just click on this funny link here, because it's the story about my heroes, as I said. So this is Frobenius and Burnside, and these are Schur and Brouwer. And the story goes a bit like this. So this is some kind of German connection here. So he was his advisor, and he was his advisor. And you will actually see in the diagrams that you can track it down. And I really would like to mention this one as well. This Burnside, he will not appear in my story today, but he was here in Cambridge. So he was a student in Cambridge about 120 years ago, and also a lecturer for 10 more years, which makes me very happy to be here in Cambridge giving a talk where one of my big heroes of all time, Burnside, was very active. And I really would recommend this book to you. So let me just click back. Okay, so we are back to Chauval duality. So we have these two commuting actions, which is basically the first statement of Chauval duality, acting on the space, and they generate each other's centralizer, which is the second statement of Chauval duality. This just means the following. This just means, let me write it down for the symmetric group, that you get a surjection from the symmetric group onto the endomorphisms equivariant under GLN of this tensor product. And vice versa, of course, they generate each other's centralizer. But somehow this is the direction I really want to use. And this is the third statement. So Chauval duality boils down to 3 statements. And the third statement gives you the explicit bimodule decomposition. In case you're worried about this explicit bimodule decomposition, it's not so important. The important part is that you can make it explicit, okay? But it's basically saying, basically decomposing it into irreducibles, in my notation L of GLN, and irreducibles of SK on the other side. But it's really not really important. Okay, so Schur already told us, well, as I said 120 years ago, this beautiful statement, which is somehow secretly behind a lot of things we actually do nowadays in representation theory and also in higher representation theory in various forms. Okay, but for today I somehow want to describe, what I really want to describe is this space, so the endomorphism space so the GLN intertwiners on, let's say, this space, and we will enrich it in a few slides. So this funny S is just a categorical version of the symmetric group. You just put at each natural number basically a copy of the symmetric group. Okay. But then what it really says is that they are computing actions, so you can use it to define a functor, right? The functor just says, so this symmetric group, the symmetric group category has just objects given by the natural numbers, and you just send the object to the obvious one, to the k-fold tensor product, and the elements of the symmetric group to the endomorphism they induce under the action on the space above. Okay, the first statement of Cheval duality gives you a functor. That's very nice. The second statement, which was the centralizer property, right? It's still written there. Actually gives you a full functor. So it gives you a full functor from the group from the symmetric group category to the representation category of GLN. And the third statement, I will not do it very explicitly. Actually, I will not do it in this talk. But the third statement, what it really gives you is a way to calculate the kernel of this functor. Something that you want to do, right? What do you do if an algebra and you have a surjection to another algebra? You want to calculate the kernel because then you get an isomorphism of algebras. You basically want to do the same. You want to calculate the kernel. You want to want out by this kernel, and you would get a fully faithful functor. And this kernel, as I said, can be basically calculated if you do your homework, sit down, and work out this decomposition. So you kill certain idempotents. But don't worry for it too much. As I said today, we will not do it. So what I would like to say here is, for this point, up to taking some, well, up to some general yoga here, some additive closures, Karubi, whatever, sure already gave us a diagrammatic presentation of the representation category of GLN. Why? Or how does it look like? Well, let me just click on this funny link here. Because you can give a diagrammatic presentation for the symmetric group, and all of you know it. So at the moment I'm unquantized, so it's just wire pictures, or however you want to call them. You have a monoidal generator, which is just a crossing between the object 2 and itself. And you have relations, the usual ones, like some Reidemeister kind of relations and some height kind of relations that I will call interchange law. So this was already known to Schur ages ago. Okay. This is somehow the starting point for my story. Okay, and I somehow want to generalize this in various directions. So let's see. So a few years later, so about 75 years later, Howe came up with a new kind of duality, or with some kind of observation how to generalize or thicken, as I would like to say. You will understand in a few slides why. The classical Cheval duality. So he actually just says, okay, we have these commuting actions. Let me first click on the link to give you the full list. Okay, so Howe actually writes down a huge list of dualities in his work, in his paper, ranging from the one I'm going to show you in a second, this one here. So those guys acting on wedges, up to various variations of it, and he's very good. So he actually does the super case. Don't worry for the super case too much, without ever mentioning the word super. So he never talks about super algebras, but he still is able to do his super duality. And he also has some BCD versions and even more versions that don't even fit on this slide. And this is somehow the real motivation, right? Coming back to my first slide. If you really read Howe's paper carefully, or Howe's lecture notes basically, then you will realize that there's not really a difference between those. There's some slight differences between those various dualities, but not much. And what we know is, in type A, from work of a lot of people here in the audience, this is quite cool and very useful, and even can be categorified in some sense, or whatever. And if the type BCD versions, they just look the same, right? So it should work in the similar way. And up to the point I mentioned before, up to my third part of my talk, it actually works very nicely, very smoothly. But I want to stress that everything is basically, so if you really want to stress it, all those webs are already in-house work. Anyway, let's go back to Howe duality, right? So I've basically, or Howe has basically replaced this side by GLK now, and you replace the tensor product of the vector representation by this tensor product of the exterior algebra of the vector representation. So this is this notation with this bullet. So just the full exterior algebra. And there will be one extra statement in the whole story. The rest is the same. They're commuting actions, generating each other's centralizer, and there is some bimodule decomposition. But there's one extra statement which will show up in a few slides again. Namely, now I want to use this action. So this guy has a weight space. So modules of this guy have a weight space decomposition, right? At least some. At least the one that appear here. And it turns out that you can write down the weight space explicitly. So we'll see an example in a few slides. So the weight spaces for some weight are just the corresponding tensor product of the corresponding wedges. There's some additional statement that Howe actually already writes down. But otherwise, it's almost the same as Cheval duality, but you have somehow replaced the symmetric group by the general linear group. Okay? Very, very similar. So this should work very similar as well. Yeah, it indeed does. So this guy is the idempotent version, and Pedro has already done all my work, so I don't have to introduce it anymore. It's absolutely the same, well, the even easier one than Pedro used in his work. But otherwise, Howe's first statement, right, there are commuting actions, now gives me a functor from this idempotent inversion to the representation category. And what does it do? Well, it sends some idempotent mu to just, the tensor product of mu1, where mu1 are, of course, my components. We'll see an example in a few slides, right? So this is the first statement. The second statement works in the same way. They generate each other's centralizer. So what's happening here is you get a full functor. Well, we already know how the third statement works. So you can mod out by some kernel, just analyzing the bimodule decomposition smartly enough. You can mod out by some kernel, and you get a fully faithful functor. Oops. Yes. And now comes this extra statement, which, well, now you want something like this wire diagrams for the symmetric group, and you should use this extra statement, Howe gives you this statement 1/2, to just define some web category. It's basically dictated to you, as I'm going to show you now. As you can see, there are funny things to click on. So I just click on so this is my first one here. So this is how the diagrammatics look like. We have already seen them, I think, for example, in Dave's talk, basically the same relations, basically the same diagrams. So you have two generators, merge and split. They go from the corresponding objects. Okay, I need some orientations, but I don't care. And you have an interchange lower, and you have those funny relations called this, associativity, co-associativity, and this funny relation called the square switch, which we have already seen in Dave's talk as well. So very nice diagrammatic category, but actually how do you come up with this category? Well, I claim it's already dictated by what Howe actually told us. So Howe told us that there is this weight space, which is now given by A1 up to AK, which are the tensor products of the wedges A1 up to AK. And he tells us this is a weight space. So Pedro reminded you how E actually, let's say E acts on this weight space, right? E acts on this weight space by the corresponding simple root in my choice of Dünken diagram. In this case, or in my notation, this would be, for example, epsilon1 minus epsilon2, which in coordinates is just 1 minus 1 and a lot of zeros. Okay, and E should act on whatever weight space you are in. so E1 in this case, by this simple root. And this just means if you put your strands next to each other, let's say A and B, and I don't care for the other ones, so C, C, whatever, then it should increase by 1 and it should decrease by 1. So what can you draw in the middle? There is only one reasonable thing to draw. You want to transport. You want to make this one thinner and you want to make this one thicker. So you just transport one from right to left. These were these ladder operators we actually also have seen in Pedro's talk. But the point is, you're basically forced to draw them in this way. Otherwise, well, of course you could think about some more complicated diagram. Why should you? But why should you? F's the same way. But yeah, so they're basically dictated by Howe. Howe says, morally says, they have to look like this. And so the definition of the web category is basically already dictated by what Howe duality tells you. Let me just repeat it again. And what you actually get here, and this is also Howe's point, so Howe argues in his paper that Howe duality is just a fancy version of Cheval duality, and this is exactly what you get. So how can you embed the symmetric group into the web calculus? We have already seen the formulas. You just send the crossing to the crossing, and the crossing is just a linear combination of the webs you all, we have already seen in definition of, for example, the skew calculus. And what it really does in the end, if you be a bit careful, then you can check that the symmetric group is actually isomorphic to the n space of the thin object, the object labeled 1. Right? So this really means Howe duality or webs are a thick version of the symmetric group. Okay? And Howe was already aware of this. He would never use the word thickened or whatever, but he basically writes that this is true. Well, up to this point, this is well known. This is all in Howe, as I said. Yeah. But it's basically a machine, right? You plot in the duality and you get out a diagrammatic calculus for intertwiners between GLN. And if you recall basically the Rashidiki-Turaev approach, that this category is where your link invariants should live, right? So should deform everything and you should get link invariants, and this is basically the idea how duality should tell you something about link invariance. Okay. Questions? Doesn't seem to be the case. So let me just, for completeness, explain actually the nice representation theoretical features that are hidden in here. They will get, well. So on the representation category, you have actually two very natural maps, which I like to draw as a merge and the split for exactly this reason, because I want to map the merge to the merge and the split to the split. But they are really just given by you take the tensor product and you realize, oh, in the tensor product of the A stretch and the B stretch, there is actually a copy of the A plus B stretch. Okay? And you can choose up to scalars the projection and the inclusion of this corresponding factor. So that's what the webs really stand for in the language of representation theory. And then this functor is not very surprising anymore. So this is basically already clear, I already said it. But it will send the merge to the merge and the split to the split. Very easy, and as I said, basically already in Howe. Yeah. So let me just phrase that all those funny relations I showed you a few slides ago have a very natural interpretation in this language. For instance, this co-associativity, they just say that the wedge space of the vector representation is a co-algebra with co-multiplications given by merge and split. Yeah. So this is basically how it works. Just to make sure that you understand. So this is my E, right? And it decomposes into those simple webs. So you transport one, and if you just slice it horizontally, so here's the first slice, here's the second slice in the middle, and this top slice, then you would see exactly those diagrams, sorry, not those diagrams, those points turning up, and the corresponding E is given by composition of the corresponding inclusions projections. And actually that's a very nice observation, because let's assume you would start with those guys here. Then you could recover Howe's action by just defining it this way. Okay? You don't need to, because Howe already tells you what to do, but you could. And this will be of some importance later. So let me just mention it here. But otherwise, a very nice story up to here. So now in the second part, so in the second section, now I'm going to type BCD. And actually, it's basically the same story. And it will connect up with Radmilla's talk, which makes me very happy. So a few years later, the student of Brouwer, actually wrote down this remarkable relationship between SOSP and what is called the Brouwer algebra. So let me click here. So the Brouwer algebra, or the Brouwer category, is basically the same as Radmilla has drawn, but somehow the biggest difference is that I like my pictures going from bottom to top. In my language, this Brouwer category, BRN, has 3 monoidal generators. One should look very familiar. And you get 2 extra generators, which we will we will see some representation theoretical meaning of these guys in a few slides. And you have some relations, like you want to remove a circle, or you have some interchange law. But funnily, so those diagrams, which are basically Radmilla's diagrams, drawn in a very weird way maybe, already appeared in Brouwer's paper, which is exactly 80 years ago. And just to say, I think, I'm not sure, of course, I never met him, but this actually tells me that he was already thinking diagrammatically. 50 years before, let's say, diagrams become more popular with a race of quantum topology. I mean, it must have been 80 years ago, it must have been horrible to try to publish a paper which is basically made of diagrams. So if you read this paper, you will see several of those diagrams. It must have been it must have been a nightmare. Nowadays, it's still a nightmare to try to publish papers with diagrams. But 80 years ago, anyway. Yes, so one technical point I should mention here. So in type A, there's a slight confusion if you want to put in SL or GL. You really should put GL, but it doesn't really matter. Here it does. So I'm phrasing everything with SO, but this is really wrong. And there's a nice reason for it that I just mentioned once. So if you take O, whatever, N, whatever, and you restrict your representation to SO, then one of them, precisely one of them, will split into 2 different copies, whatever, V and V prime. So one irreducible restricted down will split, and this will make your home spaces grow, right? And the statement will be false. This doesn't happen in type A. That's why it's basically not important if you say SL or GL, but indeed it does happen here. And of course, Brouwer was already aware of it. Anyway, so let me stick with SO and SP. But then the statement is the same, right? Brouwer gives us the same statement. This time V is the vector representation. V is still the vector representation, and the only thing you change is you replace this side by either SO or SP, whatever you like more, and this side by the Brouwer algebra, and it's the same statement. They're computing actions, they generate each other's centralizer, and there's some funny bimodule decomposition that you can use later on, of course. So this should work in the same way, right? This should really work in the same way. And indeed, you get a full functor from this Brouwer category into the representation category. And this is just, so my BN, as I said, is basically Radmilla's, I forgot what her notation actually was, but it's basically the same. And you could calculate the kernel if you're really brave and want to calculate idempotency in the Brouwer algebra, then in principle you could calculate the kernel. So what Brouwer actually gave us was a diagrammatic presentation of the representation category of Gn. In very much the same way. So Oh, advisor and the student, right? So what coming back to Howe, again, some years later, same paper. Brouwer, well, I now chose one of them, so SO. I just like, I don't know, SO, I just like them instead of SOSP. But anyway, they all work very parallel. It just gives you the same statements. They are commuting actions, this time SO and SO on the other side. They generate each other centralizer, there is a weight space decomposition. You can write down the corresponding bimodule decomposition. So one side is a bit fishy, we will come back to this in a second. So this is really not a typo, this is 2k and there's only k factors. And you can already see it here, this looks a bit fishy. But anyway, one particular point is that you somehow lose the symmetry, so you really have SON, which means even or odd on one side, and the other one will always be even. But this is just, well, it's just how it is. But otherwise, it's the same statement, so ignore the technical details, and it's the same statement as for Howe duality, as for the GL-GL duality, right? So what does this mean if we follow this diagrammatic presentation strategy? Well, this actually should mean that we would get a diagrammatic, some kind of enriched web calculus, right? Webs in types BCD. And this is how it works. So at the bottom you will see exactly the same diagram as before. And of course there are some funny links that I will click on in a second. But this is the main diagram basically. So what you do is you use what you already know, right? So you use the Howe duality in type A. And what you want is you want to describe this game here, okay? So what you do is you restrict the action on one side, that's why I call it the restriction game. And if you restrict the action on one side, then the centralizer on the other side actually gets bigger, as you can see. Very easy, right? If you restrict your action here, and you have fewer constraints, then the end space will potentially grow. And in this case, it does. Okay, but what does this mean in diagrams? This means we should get old diagram generators, namely the ones you just restrict down, but you should see new ones. Okay? So in this restriction game, it's always the same. You restrict down, you get a huge bunch of diagrams that you already understand, which will be our webs. I will click on the links in a second. And you will get new generators, like in the Brouwer case, right? Remember, you had a crossing and you had some funny new generators. So let me just click on this link how this web category actually looks like. So we have our old generators, the type A generators, merges and splits, and you get new generators like cups and caps. And where do they actually come from? Well, remember we tried to describe some representation category in types BCD. And now actually the vector representation and all its wedge powers are actually self-dual, which means you will find a copy of the trivial representation sitting inside here, and you can, and those guys should be the corresponding inclusions and projections onto this copy. But otherwise, it's really an enrichment of the old calculus, and it has some really nice relations, like the usual ones, your interchange law, and some relations I just like to draw this way. So remember that the crossing is just an expansion of in summons of webs, and it's really beautiful. So all these relations will look completely topological. You have the usual SN, so the usual Reidemeister-like thing is here going on, and it really felt somehow correct. So this diagrammatic calculus, you just enrich your already known and maybe beloved web calculus a bit, just following the restriction strategy. And actually you are forced to do, so Howe already knows how it works. So this is my choice of Duncan diagram in type D. Remember, some of my dual guy here, this one that I want to use is SO2K, which is type D. This one. So this is my Duncan diagram of type D, and Howe tells you what the weight space are, right? And how should E and F act on the weight space? They should act by the corresponding simple root. And this extra simple root, which is in black, is now not 1 and minus 1, but it's 1 and plus 1. Yeah, so plus 1 and plus 1. So what can you do if you start with AB and you know that you have to end in A plus 1 and B plus 1? So what can you draw? There's only one reasonable thing to draw, right? You open a cup. And this is my action of E. Or you close a cap. That's my action of F. Just so the only thing you can do. Here's an example, for instance. So there's this funny shift that you can ignore. It's basically acting on 0, 0. What happens if you act on 0, 0? You use E. You go to 1, 1. So you open a cup. You use F. You go to 0, 0 again, and this is a cap. Okay. So basically dictated by what actually Howe tells us to do. So there's basically no other choice, in my opinion. And also already in Howe's paper, so this web calculus is actually a thick version of the Brouwer algebra, right? And how does the functor look like? Well, you set a crossing to a crossing, you set a cup to a cup, and you set a cap to a cap. And everything thin, so with label 1. You would not be, well, you have to check, but it's not a big surprise actually that the Brouwer algebra will go, will be isomorphic to the n space of the thin object, tensored appropriately often. So up to here, let me just click back. Up to here, I think the story was so smoothly, went through smoothly. The diagram calculus is the old one, the type A webs, plus some extra stuff that you should expect if you do your homework and basically read about some representation theory in other types. So it really felt to be somehow the correct version. So as I said, coming back to my story, I was visiting Antonio in Freiburg, and up to this point we basically had it in one day. And it was a very hot day in July. Now it's 2 years ago basically. So it was 42 degrees. In case the matrix system doesn't talk to you, it should be something like 110 degrees Fahrenheit. So it was very hot. But still, it just felt naturally and everything goes through smoothly. So what we really hoped at this point of the story, yeah, we just put in some queues, as you can see there are new queues at the moment, and then play the same game. You have a type A story. Hopefully you get some Kovanov-Rosansky homologies in type BCD, which should be Kovanov-Rosansky homologies in type A plus a little bit extra, like this cap and cap. And you upgrade everything, follow the same approaches we have seen several times, which are, and get some Kaufmann homology, do whatever. But it turns out that it is way trickier than expected. I'm coming to this in a second. In some sense, our approach from the beginning was dead on arrival. So in some sense, we could have stopped right there, but we were not aware of it. So we worked very hard, or in particular he worked very hard to get the queues done. And I will tell you actually now in the last, well, roughly 20 minutes, what is the answer to how to quantize this. Okay. So third part of the story, quantization. Starting with my picture again, so my restriction game, right? That's what you want to do. You want to somehow quantize this picture because it gives you this enriched Brouwer type, Brouwer-like web calculus. You somehow want to enrich this picture. So the first thing you just do is you just quantize the corresponding representations, tensor them together. It works quite fine. For the experts, this is somehow the quantization of Berenstein-Zwicknagel. But if you're not an expert, I will come back to this later, but you really should not care. So this goes through smoothly. And then you quantize the type A Howe duality, which was done by Lehrer and Zhang. Basically, they just say, yeah, we can do it, so we do it. So we do it in half a page. Not really their point. It's it's quite easy. You just put the q's where you expect them to be, and it works. And now you think, well, let's go on to other types. And it turns out it doesn't work. So you take the quantum group on this side, and there is basically no embedding. Okay? There is no embedding of the quantum group of SO into its bigger parts, the quantum group of GL. While the other one actually quantizes. That's already weird, but it gets even weirder. So there is no action at all, as I'm going to explain in a few slides. And the other action is completely unclear, right? This was this funny action where you saw those funny irreducibles turning up. It's completely unclear. So basically, we are stuck here. We cannot play our game anymore, so we basically don't know what to do. Let me just mention, so this is part of Kupperberg's paper, which already turned up well, in Harald Miller's talk. This is part of Kupperberg's paper, and what is really behind this whole, well, we will see what is really behind this whole quantization issue in a few slides, but what I want to stress is that Kupperberg was completely aware. So we needed 1.5 years to understand what Kupperberg writes on one of his pages completely explicitly, because he writes down the quantum dimension. So in his notation, this is the vector representation, so this is double line. So he writes down the quantum dimension of SO5, which is this funny polynomial. Just look at it, it's a bit funny, right? Actually, what it really is, it's quantum n in general. So for so in this case, it's quantum 4. -1. In general, it's quantum n minus 1 plus 1. That's the quantum dimension of the vector representation of SON. Which, of course, if you don't care for quantum, you just cancel the ones and you're happy. But in the quantum case, it doesn't. It's just not true. The vector representation of quantum SON has a funny quantum dimension. Okay? And if you think about what we're trying to do here, we're trying to restrict everything down. So this is doomed to fail, because when I want to restrict the quantum representation down from GL, which GLN has just quantum 5 in this case as a dimension, you should get quantum 5, because it just should stay the same, but you don't. So this game is doomed to fail from the beginning. And this was actually quite shocking when I really realized that, because I should have read this paper more carefully. He was already aware of it, but I didn't. So what can I say? Always do your homework. But let me actually explain what comes out of this game. So just to make sure again, the quantum dimensions outside of type A, they look a little bit fishy. For instance, if you would put SP here, right? This is somehow dual of what I'm telling you. Then the quantum dimension would be n plus 1 minus 1. So switching those two signs, which again in the non-quantum case collapses to your usual dimension, but in the quantum case it's wrong. Shock. So what you really have to do, and this seems to be some kind of general feature that I'm going to explain in a second, which shows up outside of type A. What you really have to do is you put what is called a co-ideal here. I will explain what a co-ideal is in a second. Because if you put the co-ideal on, so this is my notation for the co-ideal, this is funny prime. Because if you put the co-ideal here, then Howe duality can be saved, and you actually get this diagram up to this one. So the restriction game. And then you can just play the same game again, right? And you want to look like, you want to see how your webs now look like, now that you've quantized them. Still keeping in mind that everything should give you link invariance, but it really does not. So let me just click on the diagrammatic category. So this is the corresponding diagram. Okay, so diagram generators are of course the same. But you get really funny relations. Okay? Oops. So this interchange law, it will be some kind of graded interchange law. So everything will have a degree. I haven't even bothered to write it down. But if you now do a height move, well, you pick up a factor of q. And the Reidemeister moves, well, look at it. That's not very good, right? If you want to do topology. If you kick to the right, then you pick up a q with a power depending on n, so on whatever SON you have chosen. If you do it this way, then you don't. So you just turn your hat and you have a different power of q. This is really weird in some sense, or really nice in some other sense. But so remember, this is the crossing. But what this really tells you is somehow that you should really be very careful if you try to define link homologies outside, or link invariants outside of type A. For instance, I would never check such a relation, I think. But I mean, if this is satisfied by your link invariant, but this seems to be somehow so built in. So you really should check it. That's my only message here. But otherwise, the diagram. So if you collapse Q, of course, you get the usual diagram calculus. Okay. So let me just click here. So just for completeness, right? So what you do is you restrict down the action of the quantum group GLN on its vector representations to this funny co-ideal. In particular, all the intertwiners you had before, you can restrict them as well. Okay, so you already know how they look like from the formulas. And as I said, this guy contains a copy of the trivial module, and then you compute by hand how those maps actually should act. So how do you get the projection and the inclusion onto this trivial copy? So you get formulas for cup and cap. And because of this weird action of Howe duality, it's absolutely not clear how to quantize. And the only solution we actually found is to do it, as I said, the other way around, to write down the maps and then to quantize Howe duality. So this is basically the proof, up to the fact that I don't give those guys. So you write them down in coordinates, you build up your letters as before, so those funny letters here, and then of course just, for instance, compositions like this. You know how your maps look like on coordinates, and you use it to quantize Howe duality. That's the only solution I know, because the formulas, they get really horrible. Okay, so we really, or in particular Antonio tried for a long time to compute those Qs, and it just goes crazy. Anyway, so this is the only thing I know how to do it. Some of the opposite approach of Howe's. But if you do it, you basically can use this to define the Howe action, which is, as I said, the opposite of the usual approach. Anyway, so let me comment on this guy for a second. So what is actually a co-ideal? So a co-ideal, so my co-ideal is my prime. So a co-ideal, so the first definition that I know, or usage that I know, goes back to two physicists in 1994. And the basic philosophy of those co-ideals is that if you have a Hopf algebra, like a GLN, or like this one, UQ-GLN, and there are basically no Hopf subalgebras in some way. But you have a lot of co-ideal subalgebras, which just means that your co-multiplication, it starts, well, where it should, but it does not end where it should, right? It ends, this is okay, but you only end up with one factor, in this case a left co-ideal, with one factor being in the bigger group where you ended on. And indeed, if you just, in this case, just go through what properties those guys have, this is not a subalgebra, so I cannot play my restriction game. This is a subalgebra. In contrast, this is a Hopf algebra. This is not a Hopf algebra. This means your category is not monoidal. You get this funny interchange law. But both are somehow quantizations of the same thing, which is quite amazing. So outside of type A, there is not a unique quantization anymore. And we are on the categorified level. I have no idea what to expect on the categorified level. However, this guy has the nice quantum numbers, right? So I restrict my vector representation down to the co-ideal, which immediately means that the vector representation of the co-ideal will be of quantum dimension n instead of this funny n minus 1 plus 1. This guy has extremely weird quantum numbers. And if you really calculate it through, this slight flaw, this n minus 1 plus 1, it makes your formulas absolutely horrible. It just propagates all the way through as you thicken your diagrams. Just very hard. However, in contrast, some of the quantum group gives you the written Rashidiki-Interayef invariance. The co-ideal doesn't give any reasonable topological invariance I'm aware of. So somehow two different things you can do in type A. And the Howe approach, which is so powerful is outside of type A. The Howe approach, which is so powerful in type A, it fails for a quantum reason. At least if you do it this way. But what does it mean? This co-ideal actually really means, coming back to the picture from my first slide, from my title page. Let's say it's an action, right? A left action of the web category for type A on the web category for type D. So you have some left directionness in your webs. You have an A web acting on an old part. So cups and gaps somehow are only allowed to be in one part of the game. Okay? So this is really quite weird. And of course you get some of the same statements. So for the Brouwer algebra, by the way, the same is true. There are two different quantization of the Brouwer algebra. One is called the q-Brouwer algebra. It goes back to work of Molev, which is fairly recent, compared to work of Brouwer, of course. Yeah, so in types BCD there are just several quantizations. What can we do? Well, so maybe we can do something. So let me just finish off by showing you what could be done. Also, I just heard a few hours ago that I should stop doing webs. I've done enough. So maybe I should, but maybe I should not. Let's see. So in types BCD, actually something interesting happens. So up to some details, like I don't care what to put here. So you have various ways to quantize it. So you can sandwich your Howe duality that you want, like this one, into two different, so this one is known, that's type A. This one is known, that's type A. And I showed you actually this way, so the top. But you can quantize it a different way if you want. And indeed, that's different. It gives you different answers. So that's the one I showed you. On one side, you will see this funny co-ideal. On the other side, you will see the quantum group. However, if you do it the other way around, you will see a quantum group on now on this side, and a co-ideal on the other side. Gives you again a different Q version of those web categories. And this is presumably the right one, so the bottom, but it's also harder. So it should be related to work of Hoel's and Antonio's, but it's harder, just for various reasons. Okay, so maybe instead of seeing it as a flaw, you can see it as a feature. We have various versions of quantizations outside of type A. And those co-ideals actually show up in also recent work, let's say, of Benz, but also of Michael and Katharina. And they're related to canonical bases outside of type A. Also, they have a different co-ideal, but anyway. And they seem to be easier to categorify because they have the right quantum dimensions. So maybe those co-ideals are the right thing to consider as soon as you leave type A. Maybe. As I said, they should be amenable to categorification. I have something like this in mind, I must admit. I think we will see these pictures in a few in Anna's talk again. So for Anna, Chris, and Stefan, they actually mean something different. And I just shamelessly stole those pictures. But what I somehow want is, I want some foam category categorifying these co-ideals, where whenever you basically do some height move, you should pick up a grading shift, or a factor of Q, or whatever you want to call it. So I suspect, because the quantum numbers are so nice, that everything should be amenable to categorification, and maybe also this part of the game, which should give you Kowalno-Wodzinski and Kaufman homology. Whoop. And you can do other stuff, like it seems to be very closely related to questions that arise in newer work of Bunn and Ellis, for example. So q-monoidal, supermonoidal. So in some sense, maybe it's not a flaw. Maybe it's really a feature. And what you really should expect as soon as you leave type A is that in some sense those co-ideals would sneak into your game. That's some of the message I want to communicate. So just be prepared that Q's might be weird, and be prepared that you might have to leave the familiar world of Hopf algebras, basically. Yeah, but I learned one thing, okay? Only one thing in my whole life, so never go over time. So I stop here. Thanks.
Are there any questions?
So sorry, you said that that we were working with a different co-ideal guy.
Yes.
So what's yours?
Mine is really SONGL, using the Chevalier involution.
Okay. What is that in terms of black dots and white dots?
I don't know.
Okay.
So we don't have a categorification.
But is that like? Sorry.
And it will be harder because so our co-ideal doesn't have a good Catan part. So I'm not quite sure what to do.
So it's not just the like parity. It's
No, it's different.
it's one that doesn't come from a diagram involution. It comes from color.
Exactly, yes.
Black.
It's a Chevalier involution. We can talk about it later, actually. Yeah.
Any other question?
In the A case, when you go into quantized things or so on, isn't that where the Hecke algebras?
Yes, the symmetric group just quantizes to the Hecke
Yeah.
algebra, yes.
And in this case, it's the Berman-Wenzel.
No, it's not. It's either, there are two quantizations of the Brouwer algebra. One is the BMW,
Yeah.
and one is this funny Q-Brouwer algebra. And they're not the same. One gives you link invariance, one gives you representation
I
theory.
see. Okay.
That's the whole problem, or the whole feature, whatever.
Yeah, but is the problem that you're trying to do something that doesn't get you link invariance that makes it difficult?
No.
No.
Somehow the point is if you want to use representation theory to get link invariance, very similar as you know it in type A.
Yeah.
The BMW is not the right thing, so you don't get link invariance, you get some Q funny quantizations. And I don't really know how to avoid this.
For CN, is it similar?
Oh yeah, the SP story is exactly the same.
You have to use the
Co-ideal,
reducible support.
Sorry?
The exterior representation is not reducible, so yeah.
Yes, and that's actually why. So we get a slightly different calculus, but the story is the same. So we get a calculus like this, when now the exterior is not irreducible, so you have an intertwiner to the trivial one. But it's the same. You use the same procedure, and everything looks very similar. Same flaws, same features.
Any other question? Thanks again. Can we start over in a couple of minutes?